very, very small. It expanded. This all happened about 13.6 billion years ago. And we like the Doppler effect because the Doppler effect shows that most stars and galaxies going through space are moving away from the Earth, which would explain every action has an equal reaction law unless acted upon by an outside force. So that would explain the central expansion and everything moving at a fairly equal rate from this central area. We can see the central area. We kind of have an idea where it is. There's not a lot there. Some funky way that light from the other side passes through that blank area and gets distorted. So we look at that, and that's one of the explanations for those quasars and funky light distortions. So all in all, Big Bang Theory, we like it the most. There are, I think, 5 or 6 non-theological theories out there, of which, again, Big Bang is the number one. So characteristics of stars, we're going to look at stars. We're going to base them on 2 different categories. It's their composition and it's their temperature. And the composition of most stars are hydrogen and helium. But where it's significant for us is we're going to look at what percent is hydrogen and what percent is helium. Because as we'll learn today and Friday is that hydrogen is the fuel. So most stars will start with a lot of hydrogen. And as we see stars that have more helium, then we can age those stars. We can figure out what stage they're in of stellar evolution. We can predict what's going to happen next, even when it's going to happen, and that sort of thing. And how we do that is with an instrument called a spectroscope. So we looked at the light when we talked about the hydrogen and how it is like a fingerprint for hydrogen, and when it's shifting towards the red, it's coming or going away from us and towards the blue. So that all those light, that's the spectrum that Isaac Newton came up with. And a spectroscope is an instrument that basically takes that gas and it puts it in that spectra, puts it in that alignment. And it's actually relatively simple. You can use it here. We would do a lab where I have different gas in different tubes, and you go around and you look through the spectroscope and you can identify that fingerprint for each one of those gases, from argon, krypton, hydrogen, helium, that sort of thing. Temperature, when we look at temperature, we're going to look at the color of a star. So here on Earth, if something is hot, we color it red. If something is cold, we color it blue. But that is not the case. In space, the hottest stars are blue, and the coolest stars are red. So red are cool, and blue are hot. And stars are big. It's, again, I can't wrap my very simple-minded brain around how small and insignificant we are as humans, as an Earth, as a solar system, compared to the vastness of the universe. It's just it doesn't even boggle my mind. It just shuts my mind down, and I think about toast. But I have this very quick, and you probably have seen it. I don't believe I'm sharing the sound, but it's just classical music. It's just pretty decent. But anyhow, you'll appreciate just the size of things. So it starts with the Earth, obviously, and it just compares us to other things in our solar system. And as this goes through, look at the biggest thing as it slowly starts to disappear. Y'all see the video?
Yes, we do.
Okay, thank you. But you don't hear it though, do you? Okay, so there's the Earth compared to Saturn and Jupiter. So you can just see how big Jupiter is. It's pretty huge. And then compared to the sun, which is 300,000 times the size of the Earth. And our sun is the biggest, most awesome star in our solar system, but it is very, very small compared to a lot of the other ones. So right about now, our sun is about out of sight. And now it is. So you've got Regal, the blue supergiant, and it's going to fall out of sight. So it just kind of shows how crazy big stars are. And since this video was made, there was a bigger star than Canis Majoris. Okay, we're pretty small. So the last part is just kind of makes you realize how big it is. So you're in a jet going 600 miles an hour, 700 miles an hour. And if you're going to fly around this star one time, it would take you 1,100 years to circle it once. So pretty crazy, pretty intense size of the star. And that doesn't even come close to explaining the vastness of the universe or of the galaxy. I mean, or of the nearest planet to us. I mean, that's where it gets so crazy. So redshift and blue shift, we've been using these terms for the last couple of days. Redshift is light moving away from us. Blue shift is it's coming towards us. So this is that alteration in wavelength, the Doppler effect. So red is that fire truck is moving away. Blue is it's coming towards us. And again, a little bit of redundancy here, but most stars are moving away from us. There are some stars. Hey, how are you, sir? There are some stars that are moving towards us. Galaxy Andromeda, it's coming. It's coming. It's going to smack us right in the face. So we're going to probably collide. We're on a collision course. But the crazy thing is we're going to collide with a galaxy in like millions and millions of years. And if there were humans alive, we probably wouldn't even realize it. That's how much space is between all of these stars, that these two galaxies are going to pass through each other, and it's not going to make, like the likelihood of the two stars hitting are very, very, very slim. It's just amazing how, when you look at galaxies and you look at a textbook of galaxies, you see all these stars. So there's no way you'll be able to fly through a galaxy and not hit something. But that's not the case. We're talking 200 million light years across. So it takes 1,100 years to go around the star at 500 miles an hour. It would take, 200 million years if you could travel the speed of light, which we're not even close to. So it's, again, toast. Very big. Okay, so y'all got that? Yes? No? Maybe so? See, this is where we would talk. And we would talk about it, and we would get off subject for 35 minutes.
Because Spencer's here.
I mean, yeah, but if we were in person, this is why I hesitated on teaching this, because this is such a cool opportunity to have just these huge class discussions on astronomy. But oh well. Okay, so light year, I mentioned that. It's a distance light travels in 1 year. It's 5.9 trillion miles. Alpha Centauri is Earth's second closest star. It's 4.2 light years away. So pretty far, 24 trillion miles away. So the likelihood of going to another planet it's zero. I mean, to another solar system, it's zero. It's not going to happen. 24 trillion miles is the nearest, theoretically, is the nearest planet to us. Unless we go outside of the Kepler belt and we see some of the dwarf planets and some of the planet X's that we know are out there. So, I mean, there are closer ones, but they've got to be close enough to a star that they would be livable and worth going out there after. Yeah, and we could learn how to go faster. We're learning a lot. We're learning that light isn't the fastest thing. There are things that travel faster than the speed of light, not by much, but we have that the collider that's in Switzerland, and we're sending protons around it, 17-mile track, and trying to collide and have fusion, that sort of thing, and they're timing things and are realizing that we do have the capability of going a tiny bit faster. Yeah, and that's the, if we were able to warp speed, someone said, we could even go faster. And then if you could go the speed of light, then you get into the age, what happens to, our, it's just, I don't know. It's neat because then when we look at stars, we're looking at stars that some of them are already dead. So we're basically looking at a time machine. We're looking at stars that have burned out millions of years ago, but they're so far away that it takes so long for that light to even get to us. So the chances of getting to another planet in the next 1,000 years it's possible. Who would have thought 100 years ago, 1800s, we would be where we are now? It is possible. Anything is possible. It's just amazing how awesome humans are and how smart we are and how when there's a problem, we want to fix it. Pretty good stuff. So Alpha Centauri, our nearest planet or our nearest star. When we look at other planets, we can't see the planets. They're not visible to us. The only thing we're doing is we're looking at them when they cross the star. And there will be a tiny, tiny shadow. And on that tiny shadow, we'll be able to measure it. We'll be able to figure out the distance. So when we look at that planet, that could be planet, that habitable planet, we don't see it. We're looking for that Goldilocks planet, a planet that's not too close to its star, not too far away. So if we would find something beyond the Kepler belt, which is beyond Pluto and the dwarf planets, we're not going to be able to survive on it. It's just going to be way, way too cold, even with suits. I mean, Mars is going to be, you're going to see a Mars landing in your life. No doubt. I mean, maybe I might even see it in mine. But it's going to happen. And that's just going to be things and technology that we're going to be able to use for further and more advanced travel. We're going Star Trek. All right, parallax. So when we talk about distance to stars, we're going to use this little thing called parallax. And parallax is the shift of a star because it's moving around the observer. So what I mean by that is if I, and I do this in school, but you're not in school, but you can still do it. So hold out your thumb, stretch out your right arm, and you're going to hold out your thumb. And on the other side of your room, you're going to close your left eye, and you're going to, looking at your thumb with your right eye, you're going to block out some object on the other side of your room. Okay, so everyone has their left eye closed, everyone's blocking out some object. And now just switch eyes. Don't move, but switch eyes. So you're going to see, what do you notice about that object that you were looking at with your left eye closed versus whenever your right eye's closed?
Just moved.
It
Different
shifts.
perspective because you're looking around your thumb.
Yeah, and it's not around your thumb, you're looking around your nose. So you're looking at it from two different perspectives. You're looking at it on this side of your face and then on this side of your face. So imagine your nose this is gonna be a funny video, if you took the sound out. Imagine your nose is the sun and your left eye is the Earth's position in June and your right eye is Earth's position in January. So you have a 6-month interval and we're looking at a star in 6 months and we're seeing that it shifts. And this is why constellations like Orion disappear in the summer. Gemini, even the Big Dipper moves in the night sky because our view is shifting. Now you got to do this one more time. So that same object, you're going to hold your thumb about 6 inches from your nose and then switch eyes. So what do you notice about the amount of shift that you see now?
Like
It seems to be much more.
It's much bigger. Yeah, it's a much bigger shift. So thinking about that and thinking about the Earth in June, the Earth in January, and the sun, where is a star if it moves and we don't see it in June, but we see it in January? Is it close to us or far from us? So the greater amount of shift was when your thumb was what? Close.
Closer.
Awesome. Yep. I had
So it's
4 or
far.
5 people bust out there in the chat. Awesome. So it's much, much closer. So that is why Orion, and I'm talking about Orion like you all know what it is, but Orion is a famous constellation. We'll talk about that. But Orion it shifts. It's a winter constellation. We do not see it year round. Why is the North Star significant?
It's north.
Okay, it's north of us, but that's not why it's significant, because there's a lot of stars north of us, right? It's significant because it's
The Bible.
okay. It could have some biblical, but we don't go theological here. And a bunch of you are thrown out there. It's always there. It's always north. It's always in the same position. It doesn't move, so it doesn't shift. So what we would do in class is I would hold my thumb up and you would all use my thumb and close your eyes and shift back and forth. If it doesn't move from June to January, is it close to us or far from us? It's far. Yep, a bunch of people were throwing it in the chat. It is super far. And that's why the North Star is so important, because it's a star that's always in the north, but it's always there. It does not matter the season. It's always there. And that is why we use it as a navigational tool. Yep, absolutely. If you go in the southern hemisphere, you can't see the North Star. So they use what they call the Southern Cross. It's a group of stars that are super far away and always point south. So there's a lot of stars in the night sky in the northern hemisphere, but not all of them are always there and are always north. So as you go, if you're on the equator and you're looking, the North Star is actually going to be at the horizon. And as you go to the North Pole, it'll eventually end up straight over top of you. So that shift is what we call parallax. And that shift in parallax is the apparent shift due to the Earth going around the sun. So we kind of already figured that out. So it's apparent, and things that are apparent aren't necessarily accurate. I get a bad rap of being this nice teacher. I appear to be nice, but I'm not. I'm a jerk. Your appearance does not necessarily indicate the truth. So when we look at this shift, it appears that they're moving, and they're moving through space, but they're not moving in relevance to us. We're moving around the sun. And that is going to come into huge play when we talk about Ptolemy and we talk about the heliocentric model of the solar system, that sort of thing. Because how can you tell the difference between Mars, Jupiter, Saturn, and a star? I don't know if you want to do any night watching, but you can see Mars very, very well. Jupiter and Saturn are kind of close together, and they're beautiful, brilliant looking stars. But we can tell that they're not stars if you look at them long enough over a 6-month period. And we're going to use parallax to identify that. Oh, sorry. I think there was something extra. I don't know how long that was down there. The more shift, the closer the star. Okay. So why do we find the North Star, or how do we find it? That's a good question. So the North Star is, well, who knows? Let me just throw it out there. Who knows how to find the North Star? If you would go outside tonight and you are lost and you needed to find where north is, side note, if you're lost, just sit down. Don't try to find your way out, because you're only going to get more lost. And then you're going to make me, depending if you get lost at like Humpback Rock, look harder and longer for you when I can be home sleeping. So just sit down and we'll find you. So you can look north, absolutely. But if you're lost, you don't know which way north is. So yeah, absolutely. Gray is definitely up on his astronomy. So when we need to find the North Star, it is not the brightest star in the night sky. It's actually kind of insignificant. But what you want to find is something that you can recognize, and that is this guy or girl, the North, or the Big Dipper, Ursa Major. part of the bear, the Great Bear. So the Big Dipper is always in a night sky. The only thing that changes is its position. It will rotate around. But no matter which way it rotates, if you look at these two stars in the Big Dipper, so these two stars, you're going to line up these two stars and you're going to draw an arrow. And that arrow is going to, and actually it's going to be just to the left of it, but it's going to point the very first star that you hit after you draw your straight line is going to be the North Star. Just kind of a neat little tidbit of information, because if you didn't know how to find it, not a lot of good. It's like looking up a word in the dictionary that you don't know how to spell. It used to drive me crazy. Now I just say, hey, Google, how do you spell supercalifragilisticexpialidocious? And then she'll tell me. But back then, and when I was a wee lad, they give you a dictionary. If I knew how to spell it, just fire. And that's why I think I became a teacher. So I could do the same thing that they did to me. Okay, so the North Star is so far away, it always points north. Yep, and here it is. So here is the Big Dipper. It's a little harder to see, but you have the stars that make the dip looking thing. And then we draw a line. And it's going to be, well, I went a little too far, but it's going to be that star right there that I covered up. So you draw a straight line for these two, you're going to come to the North Star. And that's how we find it. Yay. So now you can get lost. So now when your parents say, get lost, you can't. Just tell them I can't because I know how to find a North Star. Boom. Just educated you, mom and dad. Okay, sorry. Okay, so this is rotating, and it kind of shows all the stars moving, but for the most part, this is the North Star here. As we go up, it is going to be a little bit to the left or to the right of it, but oh no, now it moved. But you get the point. How quiet today. All right, so that's how we find the North Star. Yay! Stellar magnitude. So when we look at a star, we're going to look at how bright it is. We're going to look at how bright it is and how bright it appears to be. And that's going to be significant for us. So when we're looking at magnitude, we're looking at both things. So what's the brightest star to the Earth?
Sun.
Yeah, the sun. The sun is the brightest star in our sky. But obviously, according to that video that we just watched, it is very, very small. So it is not the brightest star in the universe or the galaxy. It is the brightest star in the solar system. So when we look at magnitude, we're looking at apparent. There's that word apparent again. Apparent shift, a shift that's not there. And the other one is apparent magnitude in this case. Apparent magnitude is how bright a star appears or how bright an object appears. So if the sun is the brightest object, what is the second brightest object to the Earth?
The moon.
The moon. Yeah, and it appears to be bright. Is the moon bright? Does it produce any energy? No, it does not.
It's made of cheese. Cheese has quite a bit of calories.
It does have calories, but you have to eat that. You have to
win.
eat those calories. So it's not just energy sitting there. Come on, Spencer. God.
It's
Some
like
people
it's
say
like
that the moon
potential
landing was
energy.
fake.
The moon landing was fake.
I know.
Yes, of course.
I'm trying to prove that to everyone.
It was shot in a California studio. That's why if you get a decent enough telescope, you can go and still see the Mars or the lunar rover and the flag. And the astronauts used to drop a picture of their family on. You can see all of that from Earth. But but who sells the telescopes? The government.
Exactly.
So the government puts a filter on it, and as soon as you go over and it sees the moon, it implants those things. Yeah.
Yeah. Okay. The
fact.
hologram or something.
Yeah. So anyhow, apparent magnitude. By the way, the moon landing was not fake.
Imagine you're an astronaut and you go put a picture of your family on the moon and then you get divorced.
Yeah.
I would
Imagine if you go
so
back to the
sad.
moon and somebody draws mustaches on your family.
Ooh.
Yep.
That'd be bad.
It'd be pretty crazy. Anyhow, how bright a star appears. So the moon is the second brightest object. Venus is the third. And then it goes down from there. You can see the space station. The space station is actually pretty bright. I see it almost every night. Every night I go outside and I look up and I see a satellite or I see the space station. But I do want to give you an app. And I don't have any stock in this app because it's free. But I highly recommend you on your phone, you get 2 apps. App number 1, it's called Sky View Free. Do not upgrade. But it uses your camera, and you might have already have it. It uses your camera, and you put the dot on the center, and it'll tell you what that dot is, that star. It's really, really neat. And it has a little house, because there's 100 of them. It's that one right there. It has a little house with like a little constellation above it. That is app number 1. That'll change your life. Truly, it is a great little app. It's called Sky View Free. Yeah, awesome. Some of you have it already. I have it. Like I use it every time I'm outside because I use it for 2 reasons. I always see satellites, and I'm always curious if that's the space station. So when you have it out, you can actually find the space station because it goes through the Earth. The app does, and you can see if it's on the other side of the Earth or if it's close by. And if it's close by, you can just stay out there and wait till it goes overhead, and you can maybe identify it. It looks like a plane that doesn't blink, and then it disappears before it should. So that's app number 1. The second app is just a side note app. It's called Seek, S-E-E-K. It has a leaf on it, but it is another camera app for environmental science. You can take a picture of any animal, any bug, any plant. You don't even take a picture. You just put your camera view on it, and it'll identify the plant or the animal. It's another game changer. Like my life has been altered significantly because of these 2 apps. But anyhow, so space station is fairly bright. A neat thing that happens, I don't know if you've ever seen it, you got to kind of get out of the city. But where I live pretty close to a big open field. And in the summertime, around 10:30 at night, you will see these glowing masses of light. I mean, it looks like a UFO. It almost is bright and hurts your eyes. But wherever we are, I've only seen it in Virginia, but I see it almost every evening. But where it is everything must be perfectly lined up with the sun. So the sun at 10:30, our time, is still up out west. So it's still shining really, really high above the earth. And you have airplanes that are flying at 35,000 feet, and they're getting hit with the sun, and they're reflecting that light back down to the earth. So it's just really, really neat because you just look up and see this super bright, looks like a spotlight, and that's what it is. And then it goes out. It'll just disappear whenever the sun in that airplane changes angle, and then you won't see it, and you won't see it for the rest of the night. But just kind of a pretty neat thing. But it's apparent magnitude. So it's not really that bright, it's just reflecting light. So the unique thing here is that, do I have it listed somewhere? I don't. Yes, it is. It's right there. The smaller the number, the brighter the object. I don't know why they do that to you. But so the sun is like a -26. And the moon is like a -12. And then we can't see anything beyond a 6. So anything that's beyond a 6, those stars aren't visible. And this is at 0, really decent darkness. So we have, in the East Coast, we have light pollution. It's really, really bad. But if you went out west, you could definitely see just so many stars. So I went to Glacier not this summer past, but the summer before, Glacier National Park. It's almost bordering Canada. Not a lot of people, very little light pollution. So I was really excited to do some stargazing. but the sun doesn't set out there until almost 11-ish, 11:30-ish. So, I mean, it's dark at 10, but the night sky doesn't get super, super dark until like 11. And I just couldn't stay up past 11, even though I wanted to. I couldn't. I was just, because we were out hiking every day and we were tired, and it was just, I just couldn't wait. I couldn't wait to get to bed. I'm old. All right. So that's stellar. That's apparent magnitude. Let's just do absolute real quick, and that'll be a good place for us to stop. It doesn't. It's north. So the sun is, the farther north you go, the longer your day is. So that's why in Alaska, someone asked why it sets so late. So in Alaska, it doesn't set at all. It's light 24 hours a day in Alaska. So as you move north, you get, because of the angle of the earth. So where we are, we have a certain tilt, and we're getting a certain amount of light from the sun that's up here. But directly on the top of the earth with the 23-degree tilt, they're getting full sunlight. So as you get closer to that Arctic Circle, you're gonna get longer days. So in Montana, it gets light at like 5:30-ish and gets dark at 10-ish. And then the night sky, like I said, because we were almost in Canada, then the night sky just stays lit until 11:30-ish. I mean, you turn your headlights on at like 8:30, 9 o'clock. So it's not like crazy bright, but the sky just hangs on to that light from the setting sun for a lot longer. So absolute is the truth. So it is the true brightness of a star. And what we do is we line those up mathematically, 32.6 light years away, parsec. And that is how we would look at how bright they truly are. So at 32.6 light years away, obviously the moon and Venus, they're not going to produce any light. You're not going to see it that far away. And our sun is going to be pretty stinking small. So stars are going to fall. Again, it's going to be negative is the brighter. So the brightest stars are -5. The dimmest stars are +15. That's your brown dwarfs. Our sun's a +5. So it's middle-aged. It's middle. It's just a medium. It's just an average star. Just hanging out, and just chilling. His grandma always said he would be a star. Dad jokes. Okay. Okie dokie.